I'm going to discuss the use of contingency tables in calculating, actually in applying Bayes' rule. There are other statistics that are done on contingency tables. These are discussed in Mendenhall on Chapter 9. We're not talking about those, so just follow what's here in this lecture for any problems on contingency tables. The examples here will be for medical diagnosis, but it could be applied to any to other situations too, if you have the proper mutually exclusive categories. So I'll just use this as an example, and you can translate it to something else if you need to. So we're going to look at a diagnostic medical test, and it's going to determine whether or not a person has a particular disease. So no test is perfect, right? So if a sick person gets a negative result, that's a false negative because they're really sick. So if the test comes back positive and the person is not sick, then this is, well, it's written in real small letters here, but that's a false positive. So we have a false negative and a false positive. Right. So I'm going to take these and all the possibilities, such as true negatives and true positives, and I'm going to list them together in a 2x2 contingency table. The categories are going to be mutually exclusive. Either the person is going to have the disease or not. And the rows are going to be mutually exclusive. Either the test is positive or it is negative. So here's the general form of the contingency table. Sorry. Person has the disease, person doesn't. Here we have the test is positive or the test is negative. Now if the test is positive and the person is sick, that's a true positive. If the test is positive and the person doesn't, that's a false positive. Same for the negatives. Sick person with a negative test, that's a false negative. A well person with a negative test, that's a true negative. All right, now we can go ahead and make some totals here. That's handy. This will be the total number of people with the disease, total people without, and total number of patients. It's also the total number of tests, because this column over here is the total number of positive test results, and here's the total number of negative test results. So here's a test result for prostate cancer for 100,000 patients. So here's the 100,000 right down here. Okay. And this is the results we have. 47 true positives, 3 false negatives, for a total of 50 people who really had prostate cancer. Now, how many people in this 100,000 did not? 99,950 didn't. And you can see how the test results are divided there. Now, what we're going to use the contingency table to do is calculate 4 important probabilities. One's called sensitivity, one's called specificity. The next is the positive predictive value, and the fourth is the negative predictive value. All right. The sensitivity of the test is a probability that a sick person will get a positive result. All right. This is measuring how well the test can identify the disease. So in terms of our notation that we use, probability that you will get a positive result given that the person has the disease. So that would be the true positives divided by all the people who are sick. True positive plus false negatives. Alright, this test has a 94% sensitivity. In fact, you can think of calculating it right here along this line. So this is your 47 over 50. Alright, adding those two together. Okay, now we're going to move on to the specificity. The specificity is a probability that a person without the disease will have a negative test. So in our notation, that's the probability the test comes back negative given the person does not have the disease. So that's calculated sort of right along in this column. It is the true negatives divided by the true negatives plus the false positives. So just here's your false positives, here's your true negatives, add those together, which has already been added here, and divide by the true negative. The next two quantities that we're going to calculate are the positive predictive value and the negative predictive value. The positive predictive value is a probability that given the test is positive, the person really is sick. The negative predictive value is the probability that given the test is negative, the person is really well. And you can think of those as being calculated in that direction. So that would be the positive predictive value is the true positives, right here, divided by the true positive plus the false positives. In that case, this is 58%. Alright? Alright, now the negative predictive value is right along there. It's the true negatives divided by the true negatives plus the false negatives, divided by all the negatives that there are, you see, and that's 99.99%. Okay, what is this? That's what we spent a lot of time in the last lecture calculating using Bayes' rule. If you can put it in this framework of a contingency table, like this 2x2 contingency table, then the calculation is much easier. Well, let's look at these results a little bit because they are interesting. What we had here was a test with a sensitivity of 94%. That's a that's a probability the test was positive given that the person had the disease. It had a specificity of 92%, so this sounds like a great test. But what is the positive predictive value? In other words, what is a probability that a positive test will identify a person with this particular disease, in this case prostate cancer? It was less than 1%. Right. Why is it so low? I mean, if you looked at these numbers, a positive result would seem like, oh my gosh, you've got it. But when you look at these numbers, no, it's less than 1%. The reason is that by using Bayes' rule as formulated in these contingency tables, we have taken into account the percentage of the people who actually have the disease. And when you fold that in, then you get the true positive predictive value. And now I want to repeat the calculation that we did using Bayes' rule for the test for schizophrenia that was discussed by Cohen. In this case, let's put it in terms of the contingency tables and see that we'll get the same answers, although I'm going to use slightly different numbers than what Cohen used. So you'll see the numbers are slightly different in Cohen. It just has to do with the population, not with the results. Okay, if the incidence of the disease is 2%, then in 1,000 people, 20 would have the disease and 980 would not. Okay, so I'm going to apply this to okay, there's an error on the slide. Forget that zero. I'm going to move this comma over. Oh, wait a minute. I did it with respect to 1,000, not 100,000. That was from bad cut and paste. Like I said, I could have created everything and make little robot lectures, but I'm just going to go ahead. Alright, there we go. Now it's fixed. Okay, now, so here's our numbers. We would have, out of 1,000 people, 20% will have schizophrenia, 980 will not. The test was supposed to be 95% sensitive. That means if a person had a disease, had schizophrenia, they would get a positive result. So that's really sensitivity. Here's the equation for sensitivity. We know the 20 down here. We can solve for the true positives and find that there's 19 true positives. That means 1 false negative. We do the same for the people without schizophrenia. by using the fact that the specificity of the test was 97%. That gives us 951 true negatives and 29 false positives. I like how I said that. Cohen uses slightly different numbers, but these are correct. After I scratch off 2 zeros. Okay. Now we'll calculate the positive predictive value, which is what we used Bayes' rule before to do, but we did it using normal instead of being sick, but that's okay. You can just subtract from 1, remember, because these are mutually exclusive categories. Okay, so the positive predictive value will be the true positives divided by true positive plus false positives is about 40%. Okay, the negative predictive value is almost 100%. So subtracting the positive predictive value from 1 gives you about 60% chance that a positive test that the person would be normal given that the test was positive. And that's what we got using Bayes' rule before, with a bunch of calculations and having to figure out the denominator. Again, if you can frame it into this contingency table, it's a lot easier to do the calculation, and it gives you the same values. And these are used a lot in medicine. Here's sort of a sample showing what you get here in these marginal probabilities for this contingency table. Remember, this condition has to be mutually exclusive. So how did you figure out that it was true or not? Well, you had to have some other test, right, to put people in these categories. And here's your test, positive and negative. Looking across in this direction, we're getting positive predictive value. Going in this direction, we get negative predictive value. This column, we get sensitivity. The calculation, confined to this column, gives you specificity. And now let's look at, in words, what these different probabilities mean. I've used these words before, but it's nice to have them all in one spot. Sensitivity. I know the person has the disease. What is the probability that the test will be positive? And you see how that's written. Again, remembering what conditional probability means, notation means. What's the probability the test is positive given the person has the disease? That's sensitivity. Specificity. I know the person doesn't have the disease. What's the probability that the test will be negative? Probability that it's negative given the person does not have the disease. Positive predictive value. The test result is positive. What's the probability the person really does have the disease? And this is, so probability that they have the disease given that the test is positive. Then negative predictive value, probability they don't have the disease. I'll use an in here, given the test is normal. There's your negative predictive value. Right. And the conceptual error, the one we want to make sure we don't do, is assume that these two are equal. They're not equal. Or assume these are equal. They are not equal.